Viewers reported periodic freezes and audio desync, but only in certain regions. The ingest was fine, content delivery network logs showed 200s, and CPU metrics looked normal. The real culprit: during fast camera pans, the input bitrate spiked 3x, overwhelming the H.264 encoders. Frame drops and PTS resets cascaded through the pipeline, causing stutter on every viewer. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's design a live video streaming system. At its heart, live streaming is a real-time data pipeline. It has 4 stages: ingest, transcode, deliver, and play. Each stage introduces its own failure modes, and a bottleneck in one cascades to the next. Here's a conceptual pipeline in Java. Each stage has a distinct failure mode. Ingest fails when the broadcaster's uplink drops. Transcode fails when the encoder can't keep up. Delivery fails on cache miss. Playback fails on bandwidth mismatch. The ingest pipeline captures raw video, compresses it, and sends it to an ingest server. A buffer of 2-4 seconds absorbs network jitter. Use SRT for unreliable networks and always have redundant pushes. There's no specific code block for ingest, but remember, RTMP is simple but fails on packet loss. SRT adds retransmission and encryption. Transcoding creates multiple renditions for adaptive bitrate streaming. A typical ladder includes 6/8 variants. H.264 is universal. HEVC reduces bitrate by 40% but costs more CPU. This code defines an ABR ladder with 5 renditions from 240p to 1080p. Each has a width, height, and bitrate. The main method prints them. A content delivery network caches segments at edge servers close to viewers. A cache miss forces a fetch from origin, adding latency. Prewarm edges and use tiered caching to handle flash crowds. This bash script prewarms content delivery network edges by sending a post request to the content delivery network API for each region. It pushes the first few segments to avoid cache misses. Latency varies by use case. Reducing it requires shorter segments, which increase content delivery network origin load. Always measure end-to-end latency from broadcaster to viewer screen. This FFmpeg command produces HLS with 2-second segments, 3 renditions, and low latency tuning. Notice the tune 0 latency and HLS time 2 for reduced latency. Live streaming demands real-time monitoring across the entire pipeline. Track encoder queue depth, content delivery network cache hit ratio, and viewer playback errors. Use synthetic streams to detect platform issues before users do. This Java code registers Prometheus metrics for transcoder queue depth, content delivery network cache hit ratio, and encoder frame drops. These are the key metrics to monitor. The player is the final mile. Configure manifest refresh, buffer management, and ABR logic carefully. A dynamic buffer starts small for quick startup and grows to absorb jitter. This JSON configures the player with a 2-second initial buffer, dynamic buffer up to 15 seconds, and conservative ABR that switches down on rebuffer. Minimum rendition is 400 kbps. Before drawing architecture, estimate capacity. A single 1080p stream at 6 Mbps for 10 million viewers requires 60 Tbps downstream. Always add headroom. This Java method estimates total bandwidth for a given resolution and viewer count. It multiplies viewers by bitrate and adds 20% headroom. For 10M viewers at 1080p, that's 72,000 Gbps. Secure live streams with token authentication, segment encryption, and watermarking. Use a web application firewall and rate limiting to mitigate DDoS attacks. This code validates a JWT token for stream access. It checks the stream ID and expiry. A stolen token would fail validation. This is the same issue we highlighted at the start. During a major event, viewers reported periodic freezes. CPU metrics were normal, but the input bitrate spiked 3x during fast pans, causing the encoder to fall behind and drop frames. Here's exactly why that happened. The transcoding farm was scaled based on average bitrate, but during fast camera pans, the input bitrate spiked 3x. The encoders couldn't keep up, queue depth grew, and frame drops propagated to viewers. The fix involved adding per-stream bitrate monitoring and dynamic slot allocation. We switched to adaptive GOP and implemented a backpressure signal from the transcoder to the ingest to reduce frame rate during sustained spikes. Many mobile players cannot handle high bitrate streams. Ensure your ABR ladder includes at least one rendition below 1 Mbps, like 480p at 800 kbps. CPU metrics on transcoder nodes are misleading. Monitor encoder queue depth and frame drop counts instead. Scaling on CPU alone would miss the queue buildup. Using a fixed GOP size equal to segment duration can break ABR switching on some players. Always use an integer multiple, like 1 second GOP with 2 second segments. Without origin shield, when a segment expires, thousands of edges fetch from origin simultaneously, causing overload. Enable origin shield to absorb the thundering herd. Don't rely on server-side timestamps alone. Content delivery network buffering can add 5–10 seconds of uncounted latency. Inject a clock overlay in the video and measure from a real viewer. Don't embed the DRM key server URL in client code. Fetch it via a secure API that validates the token first. Otherwise, a script kiddie can bypass your authentication. The article mentions SRT for unreliable networks and dual ingest for redundancy. This snippet shows how to configure FFmpeg to push to 2 ingest servers simultaneously using SRT, ensuring failover if one ingest region fails. The article discusses prewarming content delivery network edges, but doesn't show an API call. Most CDNs provide a REST API to prewarm specific URLs. This example uses a generic content delivery network API to prewarm a manifest and first few segments for a region. The article warns against relying on server-side timestamps. A concrete method: inject a clock overlay using FFmpeg's drawtext filter, then compare broadcaster time with viewer time. This gives true end-to-end latency, including content delivery network buffering. To debug playback issues, start by checking content delivery network cache hit ratio with curl. Use ffprobe to verify PTS alignment. Prewarm edges if needed. Let's run through some common interview questions. Explain HLS versus Dash. HLS for iOS, Dash for Android, hybrid for cross-platform. How to measure end-to-end latency. Inject clock overlay, compare broadcaster versus viewer time. How to debug regional playback failures. Check content delivery network edge coverage, traceroute, DNS routing. And a few frequently asked questions. What's the difference between live and VOD? Live is real-time, no retry. VOD is pre-recorded, can pause, rewind. How does ABR work? Player monitors bandwidth and switches renditions at segment boundaries. Why use SRT over RTMP? SRT handles packet loss, encryption works over UDP. To recap, ingest is the single point of failure. Design ABR ladders carefully. Prewarm content delivery network edges. Monitor encoder queue depth, not CPU, and don't neglect player-side configuration. Ready to go deeper? Up next, design an e-commerce platform, then design a content moderation system, then design a web crawler. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.